Lesson 1, LC-CL filter damping. In this lesson, we'll learn about the methods that are used for damping filters and how to actually design a damping circuit for them. The plot shown here is the frequency response of an undamped filter. The filter is an LC filter. LF and CF basically are the main components of the filter and their parasitics. So LF has some parasitics, DCR and the parasitic capacitance. Okay, this is the real model of an inductor, and this is the real model of a capacitor. This is the main capacitor, and this is it's parasitics. ESR and ESL are the parasitics for this capacitor. Okay. Now, if I draw the filter frequency response, this is what I get. Okay, and I get peaking, as you guys can see, around this frequency for this specific filter. The peaking reaches about 35 decibels, so that actually introduces more noise into our system than we would like. So we gotta fix that, and the way to fix that is by having a damping circuit installed next to this filter. That way, this peak can actually be damped to an acceptable level. So what are the popular or more common damping techniques that we have for LC or CL filters? We have two methods. The first one is the RC across shunt C. So as you guys can see, we have an RC series circuit across the shunt C. Okay, C is part of the LC filter. And then method 2 is RL across series L. So as you guys can see, we have an RL series circuit across the series L, or the series L. As for method 1, I'd say that its major drawback is that CD will have to be much larger than CF, approximately 3 to 5 times larger than CF. However, in most cases, this CD can be an electrolytic cap, which helps a lot. In addition to that, we can actually also utilize the ESR of an electrolytic cap instead of having a dedicated RD over here, right? However, though, the variation in ESR with time and temperature can be problematic for an electrolytic cap. So that's that. As for method 2, the major advantage of this is that LD can actually be much smaller than LF. So that's a good thing. However, the largest drawback of this approach is that the damping leg hurts the high frequency filtering performance. So each method has an advantage and a disadvantage. For this course, since I think this is the most popular method, we're gonna go with this one for designing damping circuits. As for how to size a damping circuit, well, the general rule of thumb is that RD is usually between 0.6 to 0.9 multiplied by the square root of LF divided by CF. So that gives us RD, and then CD is 3 to 4 times CF. And here's the frequency response of this same LC filter after we have installed the damping circuit for it. So we've used these equations from here to basically come up with RD and CD, and we've installed them over here. And what I did after that is I plotted the frequency response again. And now, as you can see, the damp or the peak that we had in this region is now gone. Okay, we had about 35 decibels. Now we're looking at about like 4 decibels. So this is now a much better filter, and it's not going to introduce a lot of noise around this frequency. Okay. So how can we size the damping circuit for method 2? Well, the general rule of thumb is that LD, like I said, could be much smaller than LF, such that it acts as an approximate short near omega F, and RD appears approximately in parallel with LF for damping. As for the value of RD, we can use similar equations as the ones that we have used for the previous method. However, also simulation can give the best damping resistor for a given ratio LD to LF. In lesson 2, we'll be talking about the LC/CL filter stability.